Okay, good morning, everybody. Welcome to Physics 1520. I'm looking forward to the new semester a lot myself. This semester, we're going to be mostly focusing on electric and magnetic phenomena. And I think this is some of the most interesting stuff we could talk about in physics. So I find this material extremely interesting, and I hope you do too. Electric forces are the things that hold the world together, that hold atoms together, that hold matter together. Um, and we'll find that we're also going to be talking about light in a different way, and that light has an interesting relationship to electricity and magnetism. So we have a lot of interesting stuff to talk about this semester. Before we start talking about physics, I want to talk just a little bit about some course logistics and some changes to course logistics. The first thing that you will have noticed, I think, is that there are 2 recitation meetings a week. That's the way the course is really supposed to run. The reason we only had 1 last semester is that there were space limitations on spaces that could be found for in-person recitations. And I think in part because of the flood in the physics building, which closed down some of those spaces that still haven't reopened, we now have a completely remote recitation, which means that we can meet twice a week for recitation. And we can really do a little more work on not just getting the basics down, but on actually techniques for solving problems, which I think is a really, we do still have James and Jacob as TAs this semester, fortunately. So James will join us in recitation, and you'll see both of them in lab. Yeah, definitely yay. Recitation is meeting this week. We're starting with a bang. This is going to be an interesting semester in many ways, in part because we don't have a break in the middle. And so more than ever, this course is, you have to think about this course as not as a series of sprints to tests, but more like a marathon where you just have to keep working steadily throughout the semester. We're starting on today, we're going to review a little bit, and then starting on Thursday, we're going to be talking about the most important concept in the whole course, which is the idea of fields. And it's really, really, really important to get that concept down and be able to work with it right away, because the rest of the course will build on that. And we don't want to be lost and left behind. So even more than last semester, this course just keeps building on what we've done before, and it's really important to get the basics down. So make sure that you take advantage of recitations and help sessions, tutoring sessions to solidify your understanding of the basic concepts. The concepts are going to be a little more abstract than they were last semester. And that's more challenging, but it turns out to be hugely more powerful. We'll find that this abstraction really helps us explain some phenomena that we couldn't explain otherwise. So this investment is worthwhile. There is some sort of other changes too, and those of you who've logged into Canvas may see that things look a little bit different. So let me just switch to Canvas here for a minute. Camera. Okay. Yeah. So you'll see that the the home page just goes right to course modules. Wiley, we're using Wiley Plus, but it has changed. It's a new updated implementation, and mostly that's going to be good. But we're pioneers here in using this at UNT, so there may be a few glitches. Okay, so the homework is actually right here in Canvas. Okay, so where it, and I can't actually, I can't really quite test this out as a student the way I used to be able to do. Okay, well, it should work on Chrome too, but you can try Firefox, try clearing your cache or whatever in Chrome. But anyway, here's this week's homework. We have review of, there are actually 3 things for homework this week. There's review of vectors and electric force, and if you click on that, you should actually just see these problems right here in Canvas. So, and you should be able to work them right here. So they show up as Canvas assignments. And then we'll automatically go into the Canvas gradebook and whatnot. To get to the book, you need to click on Wiley Course Resources, and you can click on a chapter, Student Resources, and the book is much better. You're taken to the full Vital Source version of the textbook, and you can do stuff like highlight the text or make. Okay, no, so if you paid for a full year, and it's asking you to pay for another year, you need to write to me, because I think the situation is that because we've changed versions of Wiley Plus, their accounting isn't quite right. And so if I have a list of people who've actually paid for a full year, I will give it to the Wiley rep, and they can deal with it. So what happened? You're saying that you can't. Oh, okay. So do. Yeah, you don't want to go to the Wiley Plus website. You want to go through the paywall here. Tell you what, I don't think I can debug this, in real time here. But if you'll send me an email with a screenshot of what you get when you try to access either the book or the homework, I'll get help. But Wiley support may also help you too. So, okay, so let's do this offline, but do email me with as much information as you can give me, and I'll try to get it resolved for you. And tell me what you're having trouble getting at, the book or the homework, okay? Okay, there's sort of one other thing to comment about assignments. So there's, what we're going to do today is we're going to review vectors and electric forces. And so there's readings from chapter 1 and chapter 3 on vectors and electric forces. There's homework on vectors and electric forces, and then the homework on electric field is from chapter 13, which I might not have put in the readings. Okay. There's also something I really wanted to do last semester, but we were so overwhelmed by technology I didn't do it, which is ask you to make a very short video, 30 seconds to a minute, just introducing yourself. And tell me your name and how you pronounce it and what you prefer to be called and your pronouns and your major and what you're interested in science. And then one thing about you that I wouldn't guess, like you're a black belt in Taekwondo or something. And you can either record it through Canvas or you can upload a recording. Okay, this is short, should take you just a few minutes to do. All right. There's one other thing that I want to show you. Let's see. Okay, here. This is what you're going to be doing in lab. We do have lab this week. And this is what you're going to be doing in lab. You're actually going to play a game called electric field hockey. And there's a puck that's charged. We can take a top view here, tilt the field so we can see there's a puck that's charged. And what you have as resources is a bunch of positive and negative charges that you can drag. .com, I forgot the .com. It's all right. You have a link from Canvas in your lab. So you can drag a charge up here, and this charge is glued down. You can see the glue around it here. And if you hit run, it affects the movable charge and you can score a goal. And you could also do this with maybe a negative charge. And suppose we put a negative charge there instead. Okay, from what we know about electric forces, they depend on distance, so it obviously goes a lot slower, but it speeds up. And you can finally score a goal. Okay, so what's the point? The point is going to be that it gets harder because things get in the way. There are obstacles that you actually have to steer around in order to get into the goal. And what I want you to get out of this is two things. One is a sense for the distance dependence of electric forces, but also the fact that in some visceral way that when something is very close, the force is large, but when it's not close, the force is not zero. Okay, so you sort of have to do a global thing, and so I think you're going to want to do this with other people. Just why we're doing it in lab, because we need to get to that point. And that's going to be an interesting thing, right? Okay, so that's what we're going to do in lab, and I think it's going to be easier to get at with doing it with other people. All right. How are we taking attendance? I'm going to take attendance the way I ended up doing last semester, which is at the end of the class. For lecture, at the end of the class, I'm going to ask you a question, and you'll just type your answer in chat. For recitation, I should be able to get it from a snapshot of the breakout rooms. Okay, we do have a, see, that's right, exactly. Some games are worth playing, maybe. I actually first wrote this game in many years ago, uh, actually in the 80s, and it ran on old Macs and PCs, and this is an updated version that's actually written in GlowScript. Okay, so so there is lab this week, there is recitation this week, and we're off to a start. Oh, the other thing that's different, about the course organization is that there are actually that we're going to have 4 tests instead of 3, and so they're listed in the calendar here. They're gonna the virtue of having 4 tests is that they'll each test covers less material. Okay, so it's not quite as much of a burden. And so what you need to do is write down the dates of the tests and the final exam now, so you know when they'll be. If we have to change one, I'll announce it, but it'll also show up as a revision to the syllabus here. So, okay, so that's the sort of outline of what we're gonna do differently. I will. Well, I want to get these problems with Wiley Plus solved. I can give you a link I'll post it in Canvas to a free version of chapter 1, so you can look at the vector stuff again until you get into Wiley Plus. But I'd like to get that taken care of right away, so that's high on my list of things to deal with coming up. Okay, so let's get started with our review. And again, the things we want to review today are vector operations and electric forces. So as we know from last semester, we're going to be working in the usual 3D Cartesian coordinate system, where we have, typically we'll have x going to the right, y going up, and that means z is going to be out of the screen toward you. And we'll find that that we're going to be working more and more. We're going to be using all 3 dimensions when we talk about electricity and magnetism. This is actually kind of a ferociously 3-dimensional subject, and so we will be working in 3 dimensions. However, when we're drawing things on paper, it's obviously hard to draw in 3D. It's easier with a computer, and we will be using VPython for that. So we'll often take 2D slices through things. We remember that a vector is any quantity that has a magnitude and a direction. And a position vector gives a position of something relative to some origin that we've specified. So if this is our origin and we have an object here, say it's a proton or something, then its position would be given by a vector from the origin. And in this case, we often call position vectors R. And we write it with the bracket notation so that it would be the x coordinate, which we'll say is 4, and the y coordinate, which is maybe 3, and in this case z is 0 because we're in the xy plane, and a vector has units. In this case, meters. So position vectors have units of meters. Force vectors obviously have units of newtons, and we'll find that the quantities we're going to be talking about most, electric and magnetic fields, actually also have units of, in a per unit charge kind of way. Okay. It's going to be very, very important to be able to get the magnitude of a vector, and the magnitude is the size, how long it is, and in general that's the square root of the sum of the squares of the components. In this case, it's going to be 4 squared, the square root of 4 squared plus 3 squared plus 0 squared. So 16 and 9 is 25, so that's going to give us a magnitude of 5, and that's still meters. And a unit vector is a vector that has a direction, but its magnitude is 1. So the magnitude of a unit vector is always 1. And to get a unit vector in the direction of our vector here, we would have r hat is going to be, how do we do that? Well, we take the vector r and divide it by its magnitude to give us the unit vector. Now remember that the things we can do with a vector include operations. We can multiply by a scalar. But we can't, and that means we can divide by a scalar because that's the same as multiplying by 1 over whatever it is. But, so we can multiply or divide. What's a scalar? A scalar is a quantity that only has one value. So a scalar has a magnitude only, but no direction. Single number. But we can't divide by a vector. That's just not an operation that's defined. So if we wrote 3 divided by the vector r, that's something we can't do. In vector algebra, that's not a thing. So when we're getting a unit vector, are we doing something okay? Well, it looks like it's all right because we have a vector here, but this magnitude, that's a scalar. So that's a perfectly legitimate thing to do. So in this case, our unit vector r would be r hat, and we pronounce it r hat, would be 430 meters divided by 5 meters, which would give us 4/5, which is 0.8, 3/5, which is 0.60, and it has no units because the units canceled out. Now, what does it do to a vector? We're going to be doing a lot with drawing arrows to represent vectors. So what does it do to a vector when we multiply by a scalar? So suppose we decided to get 3 times the vector r. That would be 3 times, what was our vector r? 430. And all we do is multiply each component by the scalar. So we'd get 3 times 4 is 12, 3 times 3 is 9, 3 times 0 meters. Okay, so we're just making it longer, make it shorter. What happens if we multiply by -1? Well, it's -1 times 430 meters, which would give us a -4 and -30 meters. Our original vector r looks like that. So -1 times r would just be in the completely opposite direction, but would have the same magnitude. Okay. So so here we have a vector that vector A that's in the direction shown. And suppose we multiply it by b, which is some positive scalar. What's the direction of the vector b times a going to be? Okay. Okay, so pretty much everybody said to the same direction, and that's right. So by multiplying by a positive scalar, we can't change the direction of a vector. The only way to change its direction is to multiply by a negative number, which will reverse its direction. We could make we changed its magnitude, but not its direction. Another thing we can do with vectors that it's going to turn out to be very important is we can add them and subtract them. So vector addition and subtraction. So addition with components, if we have 3, 4, 0, and we added a vector -2, 0, 7, we just add the x components, the y components, and the z components, so we'd get 1, 4, 7. Now, physically, when do we care about addition? Well, one thing is if we're adding up pieces of a path, for example, so if you walk to there, and then you walk to there, and then you walk to there, then we'd add up all those displacements, and we get your total displacement from the origin as being the sum. And notice that what we do to add is we put the vectors, the tail of the second vector to the tip of the first vector. So this is the tail of vector 1. This is vector 2, and we put its tail at the tip of vector 1. This is vector 3. We put its tail at the tip of vector 2. And then the sum goes from the tail of the first vector to the tip of the last vector. Okay, so adding vectors is important graphically. And you'll find that in the new version of Wiley Plus, you'll find a few problems that actually now ask you to draw vectors, which is kind of cool, and I think pretty helpful. So, but another reason we have for adding vectors is something like we found that when we were getting the net force on something, we had to add forces. So force is a vector, so here's our system S, and it's got some forces acting on it. Maybe had a force F1 that way, and a force F2 that way, and maybe a force F3 that way. And if we want to get the net forces, which was going to determine how it moves, we have to add up all those vectors to find the direction of the net force, which is what's going to change its momentum, right? So what we have to do is redraw these vectors. So here's F1, and now we want F2, so we're going to redraw F2 with its tail here, and let me see, yeah, it's about right, the right length, F2, and then we need to add F3, so we'll add that in. And so we find that the net force acting on it is the sum of all these forces, and it's going to be that vector in that direction. So adding vectors is very important, and adding vectors graphically is going to be very important. It's going to be extremely important in our discussion of electricity and magnetism because the world is full of charged particles. Okay, we're rarely, except in special cases, going to have two charged particles interacting. We're going to have lots and lots of charged particles interacting, and so we're going to have to take into account the effect of all these things, and that means we're going to have to add up the forces by adding vectors. So adding vectors is important. Vector subtraction is also very important. And what does vector subtraction get us? Well, first of all, how do you subtract? if we took 3, 4, 0 minus -2, 0, 7 with components, we'd get 3 minus a -2 is 5. 4 minus 0, 0 minus 7 is a -7. So that part's easy. What's more, what's a little harder to remember, but is extremely important, is how we do it graphically. And for subtraction, we end up wanting to put the vectors that we're subtracting tail to tail. So let's see what that would look like. And we better do it in 2 dimensions because that's hard to draw. So suppose we had a vector. So here's our vector. 3, 4, 0, maybe kind of. And here's a vector -2, 2, 0. And suppose we want to compute 3, 4, 0 minus -2, 2, 0. Well, we can work it out, and so we're going to get 5. So 3 minus -2 is 5. 4 minus 2 is 2, 0. So a vector in the plus x direction and the plus y direction. And that vector goes from the tip of, we notice the vectors are tail to tail. These are position vectors maybe. So it goes from after putting the vectors tail to tail, then the subtraction goes from the tip of the second vector to the tail of the first vector. So if we call this vector b, then this is our vector b. What does that buy us? Well, what that gives us physically is so we'll call this object 1 and this object 2. It's the position of 1 relative to 2. And we're going to be doing this a lot. Now, you remember using this in terms of gravitational forces, right? So you remember that if you wanted to calculate, so we had a planet, here's the Earth, say, we had a spacecraft, we want to calculate the gravitational force on the spacecraft by the Earth, we had to find the position of the spacecraft relative to the Earth. So we had to find this vector r. And we got that by subtracting, so that's the position of the Earth relative to some origin, that's the position of the spacecraft relative to some origin. And so this vector r was equal to the position of the spacecraft minus the position of the Earth. So that's going to be extremely important. And we'll need to be able to do that. Okay. So let's try a question. So here are 2 vectors. We have D and C. And we want to calculate the difference D minus C. In which of these situations, 1, 2, 3, or 4, does the green arrow correctly represent D minus C? Okay. Okay, we see that the most popular answer is 3, which is correct, because we put the vectors tail to tail. So they're tail to tail in either 3 or 4. In 1 and 2, they're tail to tip, and so that's not subtraction. So it had to be either 3 or 4. And now remember that that D minus C means the position of D relative to C, and so we want to start at C and go to D. We can think of it as, what do you have to add to C to get D? And so, in fact, 3 is indeed the correct answer. Now, if you said 4, you got it backwards. And you can't afford to get it backwards when you're calculating electric forces, because then your force is going to be in the wrong direction. What you're going to get here, what you've got here, this is actually, if we say that D minus C equals, we'll call it, so the vector G. So this is our vector G. This is going to be minus G. And because it's really C minus D. And that means your forces are going to be in the wrong direction, and your particles are going to attract when they should repel, and repel when they should attract. So it's actually pretty important to get this straight. There are various ways to right, we definitely want A and B vectors in grades for sure this semester. So one way to think about it is that if G equals D minus C, then C plus G equals D. Okay, so in fact, if we start here at the tail of C, we walk to the tip of C, we add G to it, now we get D. Okay, so that's a great question. How do we know which sign to give electric force vectors? Last semester, gravity always attracted. And so that is actually our next topic, is to review the electric force, which we didn't do a lot with last semester. We did some, but not. So that's a perfect segue into reviewing electric forces. So you'll recall that there are 3 kinds of particles can have 3 kinds of electric properties. They can, and we've called them because it works out mathematically. We could have called them purple, green, and gold or something, but they're called positive, negative, and 0 or neutral because that works out really well for us algebraically. So elementary particles can have positive charges. And the one that's probably the most familiar is a proton, of course. The charge of a proton is 1.6 times 10 to the negative 19 coulombs. The coulomb is our unit of electric charge. And that actually had the name. There's a constant for it. That's the good news. The bad news is that we're reusing a constant yet again. So this is little lowercase e. And so E is plus 1.6 times 10 to the negative 19 coulombs. There are other positively charged particles. We don't run into them quite as often. There are positrons. They have a charge of plus E also. A positron is an anti-electron. It's the antimatter equivalent of an electron. So it has the same mass as an electron and some other properties as the electron, but it's positively charged instead of negatively charged. Some kinds of muons can be charged, and again, they'll have a charge of plus E. So usually for a proton, we're going to write P or P plus. A positron, we're going to write E plus to show it's like an electron. A muon is, we have the Greek symbol mu, and a mu plus. A muon is kind of like an electron. It's a lepton. It's not made of quarks, but it's heavier than an electron. There are pions. There are pi plus. Okay, so there are a lot of charged particles in the world, but the ones that can occur by themselves, like protons and electrons and positrons, always seem to have multiples of electric charge that are plus E. So they're negatively charged objects. For example, an electron, which has a charge of minus E, so minus 1.6 times 10 to the minus 19 coulombs. There is an antiproton, same mass as a proton, but negative. So again, charge minus E. Some negative muons, a mu minus. Some negative pions, a pi minus, and some even more exotic particles that we may actually run into. Now, of course, protons and electrons, and then we have things that aren't charged for completeness. Well, what's a neutral particle we know about? A neutron, right? So it doesn't have, its electric charge is 0. And they don't interact with the electric interaction. So as we saw last semester, neutrons interact with other particles with the strong force. So they interact with other things that are made of quarks, like protons, to hold nuclei together. And the net charge of some object is at just the sum of all its constituent charges. So for example, a helium nucleus, which is 2 protons and 2 neutrons for helium-4, would have a net charge of plus 2e because the protons each have a charge of plus e and the neutrons are neutral. Now, to get to electric forces, we know that charged particles can interact in somewhat more interesting, varied ways than gravitational interaction. So if we have two positively charged objects, so why do we represent the particles as spheres? So it appears that these elementary particles really are sphere-shaped. So protons seem to act like little spheres. The radius, we know the radius of a proton, it's been measured, and it's about 1 times 10 to the minus 15 meters, roughly. We don't know the radius of an electron because it seems to be smaller than we can measure. So it's very, 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 very tiny. People keep trying and we just get lower limits on it. But smaller than that, smaller than that. In fact, it's really a very point-like particle. But even though protons are made of 3 quarks, they're continually moving around in such a way that the result seems to be that they actually are little tiny spheres. Now, we may, in other problems, idealize things as being spherical, but these really seem to be tiny spheres with a charge that's uniform throughout the interior of the sphere. So if we have 2 positively charged things, say 2 protons, we find that the forces that they exert on each other are equal and opposite, and that it's a repulsive force. So they actually repel each other. So positive charges repel each other. Likewise, if we took 2 electrons and we let them go, they'd move apart, and we'd see that the forces they exert on each other are also repulsive. So we say that like charges, meaning things that have the same sign of charge, repel. And the only thing that attracts are 2 particles of unlike charge. So if we have a proton and an electron, we find that they exert attractive forces on each other. So unlike charges attract. So how do we keep track of that mathematically? That's actually, it falls out, fortunately, of our force equation, and the reason that's the reason we've chosen plus and minus to represent these charges, because it actually gives us the right direction. So let's remember what we know about the equation for electric force. So what are the things we observe? So like charges repel each other, unlike charges attract, and we see that the electric force, depends on distance. So if things are farther apart, then the forces they exert on each other are smaller. So the force decreases as distance increases. So our equation for the electric force law, the force on one particle by another, actually has to account for all these things. So we want an equation that there's probably going to be some constant here, some proportionality constant. But then it has to take into, oh, the other thing we notice is that a bigger charge makes a bigger force. So if this thing had, if this particle had twice as many protons, then it would exert twice as big a force on the negative charge, and the negative charge would in fact exert twice as big a force on it. So force, the magnitude of the force is proportional to the charge. And you may remember that we typically use the symbol Q for charge by convention. So in our equation for the electric force, it needs to take all this into account and also get the right direction. So since the force is proportional to charge, meaning that a bigger charge gives us a bigger force, are we going to want charge in the numerator or the denominator? Right, we're going to need it in the denominator. So we're going to put the charge, and since there are two particles involved, it turns out just like with the gravitational force, if we're talking about the force on particle 1 by particle 2, we have Q1 and Q2 both in the numerator, because if either charge gets bigger, the force gets bigger. Now, we find that the force decreases as distance increases. So do we want distance in the numerator or the denominator? Denominator, and you're right, it is squared. And that's not something we can tell until we make careful measurements. So we want the distance squared. Now I've written it as the magnitude of r, so what's r? Well, let's say we want the force on particle 2 by particle 1. Then particle 2 is our system, and particle 1 is in the surroundings. And so the vector r points from the surroundings to the system r. And this, of course, is the position of the system relative to the surroundings. So this is the position of 2 relative to 1. So both 1 and 2 might have positions. So that would be r sub 1, that's r sub 2 relative to some origin. And this relative position vector is in fact the position of 2 relative to 1, so it's r2 minus r1. Now, here it doesn't matter because we're taking the magnitude and squaring it, right? So that's the distance. And you may remember that the constant we use is an odd looking one. It's 1 over 4 pi epsilon sub 0. Where this constant 1 over 4 pi epsilon sub 0, the whole thing, has a value of 9 times 10 to the 9th Newton meters squared per Coulomb squared. So that's our electric constant. We write it this way because it turns out that this constant epsilon 0 has a life of its own, and it will show up in various contexts. So rather than calling this a whole different constant, it's written this way. But we have one problem with this equation, which is this side of the equation is a vector, but this side of the equation is a scalar. And so what do we need to make this work? We need the unit vector r hat, don't we? So r hat. And now we've got a direction. Now, it turns out that this is going to give us the correct direction. And let's confirm this by trying a couple of cases. So, because remember that these charges have signs. So this has a, so this quantity, when we were talking about masses in the gravitational force, masses were always positive, but these signs can be positive or negative. So what determines the direction is the signs of the charges and the direction of r hat come together to give us the direction of the force. So let's see how this is going to work. Okay, so let's rewrite our equation here. So we're going to have a little room. So we have the electric force, oops. The electric force is on particle 2 is 1 over 4 pi epsilon 0 q1 q2 over the magnitude of r squared r hat, where r, the vector r, goes from 1 to 2. From system to, from surroundings to system. So let's check it out. We've got, let's suppose we have two positive charges here, and we'll call this one 1 and that 2. So we want the force on particle 2. And this should be repulsive, right? We should, so we hope that the force on particle 2 is going to go to the right. So we'll draw our vector r from 1 to 2. And so therefore r hat has the same direction as r. It's going to go like that. And now let's check out how this is going to work out. So force on 2, so we have a 1 over 4 pi epsilon 0, that's a positive number, times, we'll call this Q1 and that Q2, but they're both positive. So we have a Q1, Q2 over the magnitude of r squared r hat. This number is positive, that number is positive, this number is positive, denominator is of course positive. So basically what we're doing is we're multiplying r hat by a positive scalar. And so the result is going to be a force in the correct direction. Now, if we're calculating the force on 1 by 2, we have to draw our vector r in the other direction, and then it's going to work out. Okay, let's consider what happens with two negative charges. We have a minus and a minus. So this is a Q1, that's a Q2. Our vector r is still the same, so we have r and r hat. Here we have a 1 over 4 pi epsilon 0, that's a positive number. Now here we have a Q1 that's negative. So this is a negative number. Let's say it's negative 3 nanocoulombs or something. And we have a Q2 that's also a negative number. And we divide by the magnitude of r squared and multiply by r hat. Well, we have a negative number times a negative number, so this whole thing ends up being positive, and so we're multiplying r hat by a positive scalar, and we still get a force, a repulsive force. So what happened was it was the signs, it was r hat plus the signs of the charges that told us the direction of the force. So maybe I'll just write greater than 0 so it doesn't look like position. So now the question is, what's going to happen when we have two charges of different signs? So we have a positive charge here, we have a negative charge here. So we have Q1 is positive, but our Q2 is negative. Now we still want the force on particle 2, so the vector r is still the same direction as is r hat. But now in our expression, we have a 1 over 4 pi epsilon 0 Q1 Q2 over the magnitude of r squared r hat. Q1 is positive, Q2 is negative. 1 over 4 pi epsilon 0 is positive, magnitude of r squared is positive. So what we have here now, this quantity is going to be negative, and that means that we're multiplying r hat by a negative number. So scalar multiplication by a negative number gives us a force in the other direction, and so the force on Q2 is actually going to be the right direction. So if we're just a little bit careful, the sign just falls out correctly when we do a calculation. So let's see what that would look like if this was a proton and an electron, okay? So by the way, so the charge of a proton is very small. It's 1.6 times 10 to the minus 19 coulombs. We'll find, and we'll actually find from some of our own experiments, that the charges on macroscopic objects that we mess with in the world are on the order of, there can be a lot of excess protons or a lot of excess electrons. So for example, you've rubbed a balloon on your sweater and stuck it to the wall, charging it. The charges end up being on the order of a nanocoulomb or so, so 10 to the minus 9th coulombs. But for a proton and electron, let's put a proton at, so here's our proton. It's at location, it's at some location. Let's make an electron. There's electron, some other location. We need locations. So let's say our proton relative to some origin is 3 times 10 to the minus 6. Well, let's make them closer. So a nanometer, 3 times 10 to the minus 9 4 times 10 to the minus 9, 0 meters. Electron is a little farther away. It's going to be at, what do we think? 6 times 10 to the minus 9, 4.5 times 10 to the minus 9, 0 meters. And now, to calculate the force, of course, we need to use that whole expression, and we need to calculate not only the vector r, which is going to be, well, we want the force on the electron, so let's find force on electron. So what is r going to be? Is it going to be r proton minus r electron, or is it going to be r electron minus r proton? So do I have a poll with 2 alternatives? I have a poll with 3 alternatives. Okay. So 3 is none of the above. So think, what's the system? What's the surroundings? Okay. So most people say that the vector r, we want the force on the electron. Most people say that the vector r should be r electron minus r proton. And that's correct, but it wasn't a big majority. Now, this is something that you're going to have to get straight, and sooner rather than later. So this is because otherwise you're going to have all your forces backwards. So this is the surroundings, because that's the thing that's causing the force. This is the system. And remember that we want the vector r goes from the systems to the surroundings. This is exactly the same as it was with the gravitational force. And that's why we did it that way in the gravitational force, so that it was going to, so this is our vector r. And you can think of it as final minus initial. So r is always r final minus r initial. And initial is we start at the surroundings, and final is we go to the system, because that's what we care about the force on. So in fact, we want r electron minus r proton. Questions about that? Okay, let's actually do the calculation. Now you can do it by hand, but I would really like to encourage you to do it to do it with VPython. So let's switch to GlowScript. And let's write a program that's just called electric force. So we're going to need to calculate force. Let's make this big so we can see it. We're going to need the constant, and since the constant is called 1 over 4 pi epsilon 0, some students started writing it as 1 over 4 pi epsilon 0, which comes out to a pronounceable thing of oofpez, 9 times 10 to the 9th. Charge of the proton is 1.6 times 10 to the minus 19 coulombs. Charge of the electron is minus 1.6 times 10 to the minus 19 coulombs. The location of the proton was, what was the location of the proton? It was vector 3 times 10 to the minus 9, 4 times 10 to the minus 9, 0 meters. The location of the electron is the vector 6 times 10 to the minus 9, 4.5 times 10 to the minus 9, 0 meters. So now the vector r is the position of the proton minus the electron minus position of the proton. And now the electric force is going to be equal to, so 1 over 4 pi epsilon 0 times the charge of the proton times the charge of the electron divided by the magnitude of r squared, all times the unit vector in the direction of r. And, whoops, I'll print it. And we get a force that is, so what do we get? Negative 2.5 times 10 to the minus 11, negative 4 times 10 to the minus 12, 0. So let me record this on our OneNote sheet and then I'll switch back. And that's in newtons, of course. So here's what we got from GlowScript. And is it in an appropriate direction? Well, it's in the minus x direction and a little bit minus y. So that looks like it does indeed point from the point toward the proton. The electron is being attracted to the proton. So it looks like that worked out correctly. Okay, today in recitation, we're going to practice with electric forces and vectors. And yeah, I'll show you the code. What I want you to type for attendance is what you'd like to learn about electricity and magnetism, what you hope to learn in this course about electricity and magnetism. What interests you, what you think would be interesting, and what you hope to learn. You don't need a class registration code, so email me if you're having trouble with Wiley Plus. But you should buy Wiley Plus by going through Canvas. going there. But if you're having a problem with Wiley Plus, email me with screenshots of what you're. Okay, these are great. Some of you have some really interesting questions that relate to real world applications. Some are more theoretical. This is awesome. We're definitely going to talk about magnetism a fair amount and magnetic fields. So, all right, thanks everyone. See you this afternoon.